Cerberus takes a lot of the stuff that was in Tempo. So it has a very similar sharding scheme. A lot of the technology that was in Tempo, such as the Radix engine and all that kind of stuff, is all very similar or takes kind of inspiration from. I suppose the main difference with Cerberus versus what Tempo was trying to do is that it's a active multi-degree consensus mechanism. And so multi-degree means that you have nodes that are voting. So and then you generally count those votes, and if you breach some threshold of agreement or disagreement, which is generally a supermajority of the people who have voted, the nodes that have voted, then your transaction, your event, whatever it is you're doing, gets committed to the ledger. And if a supermajority disagree, then it doesn't get committed to the ledger. And so by driving with the supermajority and nodes voting on what they think the truth is essentially what a multi-degree consensus mechanism does, and that provides the foundation for Cerberus. Now, there's some other kind of intricacies around consensus mechanisms. You've got BFT SMRs, which stands for Byzantine Fault Tolerant State Machine Replicators, which is something that Cerberus does, but we won't get. There are similar technologies to what is at the core of Cerberus already. Tendermint, Cosmos, Hot Stuff. There's previous BFT SMRs from decades ago. There's Lamport, Paxos. There's quite a few implementations of what is at the core of Cerberus, but where Cerberus shines is by taking the sharding model that we had in Tempo and applying that consensus mechanism in a novel way so that we can scale it linearly. And so usually when you're running with 2 or 3 phase commit BFT consensus mechanisms, you have a single instance of that consensus function running, that consensus process. And what we're able to do with Cerberus is run multiple ones of them in parallel on the same machine and run machines that are running multiple instances of this BFT consensus mechanism across the network as well. So if you've got 1,000 nodes and they're all running 1,000 instances, then you have 1 million different BFT instances, which theoretically would mean you could run 1 million TPS.
You mentioned that, sort of the most important part of it is the fact that we've used the sharding techniques that we developed before for Tempo and applied it to this BFT class of consensus. And I think, one of the really interesting innovations about this is it's a system that allows, it treats the shard. The whole point of the sharding that we've been working on for quite some time is this idea of massive sharding from the beginning, not sort of trying to apply sharding as this incremental thing to an existing, you've already got a single chain that's already doing Nakamoto consensus. Let's try to add some side chains or something on that to make it scale better. The whole Radix concept is doing it massive scale from the beginning because that's where you need to go anyway. So doing that is fairly tricky. And I think one of the clever things about consensus is it's a design that allows these, millions, billions, quadrillions of parallel shards that you need to do that scalability to kind of connect and act as consensus state machines as needed. So whereas, there are a lot of, I think, kind of the traditional research and a lot of consensus is the concept is you have one state machine, it's conducting consensus, it's going on to the next step, very blockchain-like. This is saying, well, look, you can do most of this stuff completely in parallel, it's not related. But what we do is, I think a lot of the consensus design that you'll see in the white paper is linking together these shards only whenever you need to and having them kind of act like a single consensus machine for a limited period of time before they split up.
Usually, when referring to the kind of consensus mechanism that Cerberus is, people say BFT, and then you've got Nakamoto consensus. And so BFT actually means Byzantine fault tolerant. And so Bitcoin is Byzantine fault tolerant, as are all of the blockchains. So it's not really the correct term. I've seen some comments on Telegram where people said, "Oh, it's BFT, so it's nothing new, it's blah, blah." And it's like, well, actually, you're actually just stating a function of the consensus mechanism, which is that it's Byzantine fault tolerant. Mm-hmm. So the correct term is 2 and 3 phase commit multi-degree consensus mechanism, but that's a bit long, so everyone just shortens it to BFT generally.
But can you give me, and this time I'm going to hold you to it, a 1-sentence description of why Cerberus is exciting?
As far as I'm aware, it's the first 3-phase commit sharded consensus mechanism that can do linear scaling.
It's a secure, fast consensus system that gives you linear scalability for billions of users. This is really what it manages to deliver using a lot of our own innovation, as well as some of the best research that's going on in the field right now, kind of collecting it all together. That's why it's exciting to me.
What Cerberus can do, there are a lot of questions around what from Tempo has remained. So we've got sharding being one of the main ones.
Yeah, the shard model. It's slightly tweaked with Cerberus as well. So it's gone through some improvements while we had the opportunity. There were some pending ideas that would just have been very difficult to shoehorn into Tempo as it was. So Cerberus was an opportunity for us to make those improvements.
Other than sharding, what else is?
So the Radix engine, of course, plays a big part, even though it's not seen and it's not really a thing. It's more of a theoretical, abstract thing. All the kind of data architecture that Tempo brought along, all that kind of that stuff on how things are stored to the ledger, how things are referenced, how things associate with each other. That's very key to being able to do this. I would say probably the most important thing is the data architecture and the sharding model that allows you to get to this linear scalability, because without them, you just couldn't do it. Less exciting stuff around the networking layer and messaging and all that kind of stuff that we spent a lot of time optimizing over the years. All that's obviously come over as well and gives a nice solid foundation for us to build up on top of. Innovations that we did in the gossip mechanism is very useful. Logical clocks also play a role. Like just tons and tons of the Tempo stuff comes over. Those concepts around separating related and unrelated transactions also play a very big part in being able to achieve this linear scale.
How does Cerberus reduce risk and improve implementation timeline?
There's this piece at the bottom that's very risky to mess with. And if we can use something there, then we can apply all of the huge amount of innovation that we brought into Tempo and wrap it around that kernel. And this both reduces the amount of risk that machine is going to operate exactly the way we expect it to every time, as well as reducing our implementation risk. So it's a win-win.
Whereas with Cerberus, we can go for a single instance Cerberus process per machine, and then we can scale that up to multiple Cerberus instances per machine on a later job once we've done that work. And then the third stage of that is, okay, now we can have multiple instances per machine and a sharded network too. So all different nodes are serving different portions of the ledger, and that's kind of stage 3. Instead of having to do everything right first time, we can baby step it through to make sure that the network is secure and that we are catching things that we should be catching and that nothing gets missed.
Yeah, Cerberus is really nicely modular in that way. It very cleanly separates Sybil, it cleanly separates your consensus and the sharding layer, all those things. We can roll those things out step by step and be really confident in what we're doing.
Are there any scalability limitations? Are there limitations around running a node? How does that come into play?
I wouldn't say there were any limitations around scalability. It's designed to be linearly scalable. So your limitation is basically how many nodes you can throw at the network. That's your kind of ultimate limit. There are some considerations and there are some things that we still need to figure out for the later RPN releases around things like message complexity, and do we want to use these things called threshold signatures? That basically means that you can capture more votes in a small amount of data when you send a message, so that it doesn't bottleneck everybody's bandwidth or their CPU and stuff like that. But they're all kind of more practical things. They're not really limitations to the theory or to the architecture as such. And even if we were to go with a less efficient kind of signature model, for example, then you just throw more nodes at the network and you can still achieve your scale. How efficient is it per node? And then the other lever is how many nodes in the network do I need to have in order to hit that target threshold of throughput that I'm looking for. So in terms of scale, there's not really any upper bound on how fast these things can go. It's more about how fast can the individual nodes go, and that kind of dictates things like how many nodes can collaborate together to come to consensus, What's the throughput of those nodes? How many consensus processes can a node be part of at any one given amount of time?
And the shardability kind of addresses that as well. I mean, you look at something like EOS, where they put a lot of work in making sure that they've got their what is it, 23 or whatever validators
21,
are.
I think, isn't
21, yeah. They're on these very high bandwidth links, and they're closely connected together. Like they've really focused on optimizing how the performance of those 21 nodes, which is one way of approaching it. But I mean, what we're doing is basically saying, well, once this is sharded, you don't need to worry about that anymore, because you're just going to have you just parallelize. Parallelization is the name of the game for reaching scale.
Absolutely.
What are the security limitations of Cerberus?
The security threshold of Cerberus is that if I've got more than 33% of all the vote power in the network, then I can basically control the network. I can install what's called liveness, and I can break safety. Liveness is where things continue to happen. If you stop that, nothing in the network happens. And safety is a double spend, for example, right? And that's largely the same for all multi-degree consensus mechanisms. The upper bound on security is 33% of Byzantine tolerance. For Nakamoto style consensus, it can be higher, but there's usually some trick you can do to bring it back down to a 33% kind of rule. So a 51% attack is only true under certain operating conditions. So generally, if you've got somebody somewhere who owns 33% of compute, of economic votes, of anything, 33% of votes by any means, then they win. Where potential issues come into play with things like Sybil is that proof of stake, if I have deep pockets, I can acquire tokens, and there's no real limit to how many tokens I can buy over time. And you generally, with that kind of Sybil protection mechanism, as we've seen with mining and with proof of stake, is that you just generally tend to get a centralization, right? The rich get richer, whether it's economic power, compute power, whatever it is, especially if you have a competitive reward scheme as part of your economics. If you took the block reward away from Bitcoin, then the centralization of Bitcoin would look completely different. The same with various proof of stake models. You take the block reward away, and your proof of stake centralization would also look different. So that's something we've still got to kind of dig into and figure out what that looks like on Cerberus using proof of stake, figure out, does it centralize, or is there any reason for it to centralize? What are the incentives that make it centralize, and how does that affect things?
Thank you guys for jumping on.
Bye.
Bye.